This video uses one method to calculate the Christoffel symbols for spherical polar coordinate space. It uses the example of transforming from Cartesian to spherical polar coordinates to show how basis vectors change from point to point in the space. This video is a follow-up to a previous video which showed two methods for calculating these symbols and is entitled Calculating Christoffel Symbols. So let's begin by transforming from Cartesian coordinates to spherical polar coordinates. So our Cartesian coordinates, and we transform to spherical polar coordinates, and these are given by these relations here. The position vector in Cartesian space is given by this object, the usual one, and in spherical polar coordinates that becomes this object here. Now the basis vectors in this spherical polar coordinate system are given by dr is E subscript r as the basis vector in the r direction, the radial direction, this one in the theta direction, and this one in the phi direction. And they're the partial derivatives of the position vector with respect to the particular coordinate. Alright, so just a reminder, we'll keep the position vector up here on the top of the page, and then our new basis vectors in the spherical polar coordinate system are E subscript r, dr is this object here, just the partial derivative of this with respect to r. In the theta direction, the basis vector is the partial derivative of the position vector with respect to the variable theta, the coordinate theta, and that gives us this object here. And then over here, the next one in the phi direction is the partial derivative of the position vector with respect to the phi coordinate, and that's this object here. Using this one. Alright, next, these basis vectors tell us about the geometry of the space through the metric G subscript AB, both lowered indices in the covariant position, and that's given by this object here, which is the scalar product of the basis vectors. So each element of this matrix is the scalar product of the basis vectors. And in spherical polar coordinates, when you carry out these operations, you'll find the off-diagonal ones are 0, and only these diagonal ones have values. So the radial basis vector dotted with itself gives 1. Theta vector dotted with itself, basis vector dotted with itself gives r squared, and for the phi direction we get r squared sine squared theta. And just labelling each element of that matrix according to its part in the metric. Here they are. Alright, now we can use the basis vectors in our given coordinate system to determine the Christoffel symbols of the second kind. And the Christoffel symbols of the second kind are the partial derivatives of the basis vectors in the given system with respect to each coordinate. Now it's how these basis vectors change in a given coordinate direction that gives us this object over here, the Christoffel symbol of the second kind, and we expand that in terms of the original basis vectors. So how much the basis vector changes in a given coordinate direction on a manifold or a space is given by this object here, the Christoffel symbols, that tells us how much they change. So for example, the radial basis vector, take partial derivative of that with respect to the coordinate phi, dd phi of, here we are, this is the basis vector in the radial direction, this object here, partial derivative with respect to phi gives us this object minus sine theta sine phi ex plus sine theta cos phi, and ey, and we note that that is 1 over r times the basis vector in the phi direction. So that's how the basis vector in the radial direction, when differentiating with respect to the phi coordinate, gives us this object here. And that, so here we are, and that tells us that the partial derivative of the basis vector in the radial direction with respect to phi gives us this object here, r and phi. If we follow the rule here, AB in the lower indices, so r and phi in the lower indices gives us r phi here, and then we expand it in terms of c and c. But if we equate this term with this one, because they're both the same thing, then we find that this Christoffel symbol of the second kind must be equal to 1 on r for this case. And that's how we'll proceed to find all the other Christoffel symbols. So let's go on. For instance, in the radial direction, differentiating the basis vector in the radial direction with respect to r, ddr, here it is, this is e subscript r here, gives us 0. But this partial derivative is also equal to this. And so when we expand out, we're summing over c, one index upper, one index lower, so we sum out c, so that gives us r here, theta, theta, phi, phi, and that's all equal to 0. Now the basis vectors are not 0, so that must mean that in this case the Christoffel symbols of the second kind are all 0, all three of them. So that tells us that these, c is a placeholder for the different coordinates, there you go, is 0, and that's true for all c. And that's because the basis vectors are not 0, so it must be that the Christoffel symbols are 0. Next one, let's try it with respect to theta. And here we go. Partial derivative of that gives us this object here, which turns out to be 1 on r times e theta. And that's equal to this Christoffel symbol of the second kind times the basis vector here. So that implies that gamma theta r theta is 1 on r. Let's look at the basis vector in the theta direction and take a partial derivative with respect to the radial coordinate r, and we get ddr of this object, and that gives us this, which is 1 on r times e theta. Now that's equal to the Christoffel symbol of the second kind times the basis vector, so that implies that this Christoffel symbol, theta r theta, because there's a theta here, so there must be, so if there's a theta there, that c there must be the same as that one there. So we theta r is 1 on r, and we keep going. Now, same basis vector, derivative with this partial derivative with respect to theta, this object here, and that gives us this, which is minus r times er, and that's equal to this Christoffel symbol times the basis vector. So that implies that r theta theta, gamma r in the upper index, theta theta in the lower one must be equal to minus r. Same basis vector again, partial derivative with respect to the phi coordinate, here we go, that object there gives us this, and now it turns out a little bit of playing around, you'll see that e subscript phi times cos theta on sine theta will give us this object here. So that tells us that this Christoffel symbol is this one, is equal to cos theta on sine theta. Next one, the basis vector in the phi direction, partial derivative of that with respect to r, that's ddr of this object. That gives us this, which is 1 on r times e phi, so this Christoffel symbol then must be 1 on r. Same basis vector again, this time partial derivative with respect to theta, this object here, dd theta of this, gives us this one. And again, that's cos theta on sine theta times e phi. So that this Christoffel symbol is cos theta on sine theta. Again, this time the partial derivative with respect to phi of the basis vector in the phi direction, here we go, that one there. When we take out, when we do this partial derivative of this object, we get this object here. Now this one involved a little bit more playing around. It doesn't easily match up to something. We've got, notice there's no z component part of it, so if we, by playing around a little bit, you'll see that, and they're both negative in front, so it's not as though we've got some version of this again. We haven't. What we can do though, if we go back to the first two basis vectors, one in the r direction and one in the theta direction, what you'll find is that if you multiply this n term by something, and then this n term here by the same amount, and add them together, they will cancel out, and that tells you what you need. So this vector needs to be multiplied by minus r sine squared theta, and this one needs to be multiplied by minus sine theta cos theta. And if you just look at this times that, and then this times that, and add them together, they will cancel out. And it turns out that this times each of these, and this times each of these, then add them together, you'll get this object up here. So there's a little bit of playing around there, and this, in the end, that produces minus r sine squared theta with the times the basis vector in the r direction, the radial direction, and this minus sine theta cos theta times the basis vector in the theta direction, and gives you this object here. Gamma c phi phi e c, and now we expand it out because there's two of them. There's one r, so both the c's here become r, an r term, and the theta here, both the c's here become theta, so we produce these two here. And when we equate equate them to this object here, then clearly gamma r phi phi must be that object, and gamma theta phi phi must be this object. And so we have these two here. It turns out everything else must be 0. So all of these other ones, which didn't show up as in the early workings out, because they're 0. And so what we have then, when we go through all the possibilities we have, we end up with all of these, many of which are 0. And that's our Christoffel symbols of the second kind. And remember, the Christoffel symbols represent how much a vector changes, how much the basis vector changes from point to point on a manifold. And if you look at the first video, I went through all of that.